Okay, number 13. In a sample of 2,400 people, 1,482 were found to have the dominant taster phenotype. Assuming that the population is in Hardy-Weinberg equilibrium, approximately how many individuals in the sample are expected to be heterozygous at this allele, at this gene here, task 2R38. Okay, let's go back and look at this taster allele over here. This is the chart that's kind of showing us the differences in these genes. This codes a receptor protein that influences the ability to taste bitterness. The gene has two alleles. This is the important part. A dominant wild-type allele that allows the tasting of bitterness, and a mutant allele that interferes with the ability to taste bitterness. So dominant allele, you can taste. We'll call it R. R. R is going to be a taster. Taster. Apologies for the handwriting here. This is a non-taster. This is a non-taster. Okay. So, in a sample of 2,400 people, 1,482 were found to have the dominant taster phenotype. Dominant taster phenotype. So they seem to have this phenotype, meaning that they were either big R, or big R, little r. So, in order to find, we're assuming this population is in Hardy-Weinberg equilibrium, we don't find out how many individuals are expected to be heterozygous. So we're looking for this number of individuals. Of course, we also have, and we'll need this, the non-taster. Of course, a lot of times when we're talking about Hardy-Weinberg, we want to find our Q squared, right? Remember, this is Q squared. This is 2PQ. And this is P squared. So we've counted these individuals. We know that so far from these two, we have 1,482 people that are this phenotype, right? These are both the taster phenotype. Now, as far as this bottom one, how many does that leave us? Give me 1 second while I pull out my calculator. Okay, so out of our population of 2,400 people, if we take 2,400 and subtract all of our tasters, all 1,482 of them, we should get 918. 918 of these double recessive, these homozygous recessive genotype here. Of course, that means that Q squared in our scenario here is equal to 918 divided by our total number, 2,400. That's going to give us the frequency here. That is going to give us, let me go ahead and calculate that. So this is going to give us 0.3825. Okay. Now, if we square root both sides here, square root this, that should give us Q, which is going to be important to solving the rest of this problem. So, the square root, let me calculate this very quickly here. Square root of this gave me around 0.62, something like that. I'll put 0.62 here. So if Q is 0.62, what does that mean P? As we know, P plus Q equals 1. Well, let's subtract 1. We get 0.38. 0.38 for P. Okay, so we want to find how many we would expect to be heterozygous. Of course, we have our alleles. over here, those little box over here. Now we also have, if you'll remember, when we expect certain frequencies due to Hardy-Weinberg equilibrium, these are going to be our genotype frequencies. I'm just going to put GT, genotype frequencies here. Okay, we have P and Q. We're looking for the heterozygotes, right? What percentage will we expect to be heterozygous? In order to get that, we multiply P times Q times 2. We get 0.4172. Or 0.4712, rather. 0.4712. If we multiply this frequency right here back into that population, let's see what we get. So we take this, this is a frequency, so we can multiply this directly. 0.4712. What we're really saying is about 47% of this population should be heterozygous. So let's multiply this back into the original population of 2,400. And we should get something. I got on my calculator, I got like 1131 or something like that, which is close enough. Of course, I rounded P and Q quite a bit, but it's close enough to this answer right here. And this is the correct answer. So basically what we did is we had our dominant phenotype, just to sum up here, we had our dominant phenotypes up, which results from the genotype big R, or big R, little r, and we had the number of individuals, right, out of our total of 2,400. We found out how many individuals in our population would have this homozygous recessive phenotype, because that's how we're going to find our frequency of individuals, so that we can find Q ultimately, right? We take that, we square root it. You can square root from here if you have a calculator that will do that. I'm working with my iPhone calculator, so I just calculated it out. You square root it, you find Q. From Q, you can find P, and then everything's unlocked. 2 times P times Q, 0.4712. You can multiply that back into the original population, and it will give you, out of these 1,482 people that are the dominant phenotype, the amount that you would expect to be heterozygous. So, and that number is 1,133. I hope that made sense.